Okay, let's look at the slopes of secant and the tangent lines. All right, so let's look at this picture. All right, so this black curve is the graph of, say, f of x. All right, then we want to find the slope of the secant line first. Secant line, just take 2 points. So say first point is a comma f of a. And a second point, I'm going to move to the right by 8 units, so a plus h, comma, f of a plus h. So you have 2 points there. All right, so once you have 2 points, all you really have to do is use the slope formula to find the slope. All right, so basically rise over run. So maybe I'm going to label these. So this is going to be my y2. This is going to be y1. Right? So A is the x1 and this guy is x2, right? So so y2, which would be f of a plus h minus y1 is f of a, right, over x1, x2 would be a plus h minus x1 is a. So we can cancel a's and a's. What you get is f of a plus h minus f of a over h, right? And we've seen this expression before. Remember, this is called the this was called the difference quotient. Difference quotient. All right. So difference quotient is the slope of a secant line. All right. So finding the slope of the secant line is fairly straightforward because we have 2 points to look at, and just a slope formula will get you there. All right. But the main question is, how do we find or define the slope of tangent line? All right. So tangent line will look kind of like this. So tangent line is going to be like this. So you have a point here. Let's say tangent line at a comma f of a. So this is going to be a line that touches the graph at that point. So it looks more or less like this. Right? So this is our tangent line. Right? And I forgot to label. This is secant line. Right? Then the problem is you can see that there's only one point that we know, which is a comma f of a. So there's no second point. So we cannot use the slope formula. We need 2 points to use the slope formula. All right. So what we do is try to approximate the slope of the tangent line using secant line. All right. So I'm going to call this first secant line. I'm going to call it the secant line number 1. All right. What if I move this second point a little closer to A? So for example, to the first point. So let's say I'm going to take this point right here, right, a little closer, and then form a secant line. So it's going to be probably like this, right? So this is going to be my secant line number 2. All right, and you can see that this is the first secant line. This is the second secant line. All right, by putting the second point closer to the first point, secant line gets closer to tangent line. All right, so we can get greedy. Why don't you put the second point even closer to the first point and take a point around here, and then you have a third secant. It's kind of hard to see. Right, this is going to be secant line. Sorry, why did I say SE? Sorry, secant line. So secant line number 3. All right, so secant line number 2, secant line number 3. All right, so you can see that the secant line number 3 is even closer to the tangent line. All right, so how do we say that mathematically? All right, so we know how to find the slope of the secant line, which is the difference quotient. So f of a plus h minus f of a and divided by h. All right, so putting the second point closer to the first point is the equivalent of saying, all right, h is the difference between the x coordinates of the first point and the second point. So what you can do is we can make that difference smaller by sending h to 0. So all you have to do is just to take the limit of the secant line as h approaches 0. Right? So this is the definition of slope of the tangent line. Right? So which is basically the limit of the difference quotient. All right. So let's look at an example here. So let's look at the really simple function. This is just a quadratic function, x squared. And let's try to find the slope of the tangent line at x equals 1. All right, so let's do that. So following the definition, right, so it's going to be a limit, and as h approaches 0, all right, and f of a plus h, in this case f of 1 plus h, so plug in, maybe I should write that here, so f of 1 plus h minus f of 1 all over h. Right, so this is going to give you, right, so you have a limit as h approaches 0. Right, f of 1 plus h is plug in 1 plus h here, so 1 plus h squared is, I'm going to go ahead and multiply, I'll probably write it out, so 1 plus h quantity squared minus, all right, plug in 1, so it's a 1 squared over h, right, which is going to be limit h approaches 0. All right, h plus 1 plus h squared would be 1 squared is 1, 2h plus h squared. So if you multiply that out, you get those three terms, and a minus 1, so subtract 1 over h. Right, so you can cancel 1 and minus 1. Right, and try to clean up a little bit. You can see that both two terms that's left over, 2h and h squared, both have h in it, so it's going to be limit as h approaches 0. All right, so h is factored out. All right, so you have a 2. All right, h is factored out, so it's going to be h all over h. So you can see that h on top and h on the bottom cancel out, and what you get is basically plug in h equals 0. So it's going to be 2 plus 0, which is 2. Right? So this is the slope of the tangent line at x equals 1. Alright, there are a bunch of different ways to say slope of the secant line or slope of the tangent line, and I'm going to mention for slope of the secant line, sometimes people call average rate of change, right? Rate of change, right? If original function happens to be a position function, you can also call it the average velocity. is equivalent to slope of the secant line. So if somebody say average rate of change or average velocity, then you can think of them as slope of a secant line. All right, slope of the tangent line, equivalent term would be instantaneous rate of change or instantaneous velocity. So I'm gonna be the instantaneous velocity. All right, so if you see instantaneous rate of change or instantaneous velocity, you can always think of it as the slope of the tangent line. So the way you compute it is take the limit of difference quotient. Right? That's it. I hope that this was clear.